So today we wanted to talk about the valency of atoms, and I prepared some general notes. You see, this concept of valency or valence, same thing, was actually developed before the introduction of the electron, before the discovery of the electron. And it was because scientists, chemists especially, had noted that in compounds, the atoms combine with other atoms in very small ratios. So atoms in general combine in ratios of small whole numbers. So the way that these atoms combined was, of course, of great interest to chemists. And they needed to develop something like an accounting system to that tells them how these atoms combine. So this combining power of elements, or the combining ratios of atoms, is where scientists needed to assign some numbers to know what is happening. So they assigned numbers, which we call the valency of an atom, or the valence. It's the same thing, the valence. Is what we need to talk about and what it means today. So since the late 19th century, the late 19th century, scientists know that hydrogen, for example, hydrogen in general combines with just one other atom. So with very few exceptions, of course, but nevertheless, the norm is that hydrogen combines with just one atom, one and only one. So they assign the valency of 1 to the hydrogen atom. Now, an oxygen atom, though, can combine with 2 other hydrogen atoms. The nitrogen atom, a nitrogen atom can combine with 3 hydrogen atoms. The carbon can combine with 4 hydrogen atoms. So they assign the numbers of 2 for oxygen, and 3 for nitrogen, and 4 for carbon. And these numbers are the ones that we called since then the valency of these atoms. 2 for oxygen, 3 for nitrogen, and 4 for carbon. Which means those numbers, those valencies, actually represent how many bonds these atoms can form. So in general, we can say, well, since the 19th century, the valence of an atom is thus a number which indicates how many bonds this atom can form. Now, the truth is that this system of assigning these valencies to atoms sounds a little bit simplistic in our days to us, because it applies only if the atoms form single bonds with other, through single bonds with other atoms, which we know is not true. So obviously there is a need for a new rule, and especially when later on in the early 20th century, with the discovery of the electron as well, and more insight into how atoms combined. So now, if we want to move a little bit further away, when atoms form double bonds, like in the case of carbon dioxide, this is supposed to be the representation of carbon dioxide. We see a carbon combines with 2 oxygen through double bonds. Like these little lines here represent the double bonds. So double bonds are assigned, reflect two bonds, two valencies. So double bonds should reflect double valencies, two combining powers of the carbon atom. And similarly, triple bonds should reflect 3 valencies. So if we look at the case here of carbon dioxide, since it has two double bonds and each double bond represents two valencies, we assign the valence of carbon to be 4, which agrees with the previous kind of the previous valency of carbon assigned to carbon from the late 19th century. So nowadays, in other words, we consider double and triple bonds to represent double valencies or triple valencies, respectively. Anyway, so the atoms, well, now that we have an idea of how the periodic table looks like and the meaning of the groups, the different groups, we can say that atoms of elements in the same group have the same valence or valency. Okay, this is the same valency, which we call the normal valence. And in fact, groups, the main groups, the principal groups in the periodic table, which is the first, the second, and then the number 13, 14, 15, 16, 17, 18, with a newer system of numbering them. So the principal groups have the valence of the valencies of atoms, of elements in the same group are the same. In the middle of these groups in the middle, which represents the transition elements. Transition elements in general can have different valencies. So we say, let me read what I'm saying here. Some, however, that means some elements have different valencies depending on the compound which they form. Such atoms are said to exhibit variable valency, which is the case usually with the elements here, the transition elements from group 3 up to this group there, group 12. So virtually all transitional elements have atoms of variable valencies. Notably, we are going to meet iron very often, has different valencies. It can have a valence of 2 or a valence of 3, for example, but we are going to see such cases. So anyway, the moral of the story is that in the transition elements, we cannot assign one particular normal valency because they can have variable valencies. They are peculiar elements. So this table here now, roughly, shows the normal valencies of atoms in the principal groups. So we see that the group 1, all these atoms of the elements of this group have a valency, are assigned a valency of 1, plus 1, positive valency. The group 2 have a valency 2. Now the group 13, or the old group 3, these atoms here have valencies 3. This group, starting from carbon, which is a very important group, can have valencies of 4 actually. Forget about the -4 for the time being. It's mostly 4. That's the normal valency of these atoms. Then the next group have valencies of -3. Next, -2, -1, and of course, at the end we have the noble gases, the noble elements, which are assigned the valency of 0, because they do not form bonds. Now, in nowadays, we also know that, and in fact, this is what is the meanings, the message sent in your books as well, that the valencies that we assign to atoms are actually correspond to the charge that the ions can form. So in the first group, the group 1, for example, lithium or sodium or potassium, whatever, when they form groups in ionic compounds, for example, all these atoms become ions with a charge of +1. And note that the charge of their ions actually represents all these numbers agree with the number assigned to the valency of these atoms. So roughly speaking, we can play it safe if we say that the charge that these ions, that these atoms have when they form ions is the same like the valency, which is actually quite convenient for us to know what the charges of the atoms are, or if we know the charges of the atoms of the ions, we can tell the valency. So these numbers actually can represent the charge of the ions when these items, when these elements combine and form ionic compounds. And that is why in your book, they're on page 75, they start by talking about, if you look at the heading, it says the formulae of ionic compounds. They start from ionic compounds because it's easier to introduce the valency of elements through the charge of the ions. But next we're going to see that to find the formulae of covalent compounds, we use the exact same rule, really. So anyway, it's just because of convenience that they start by the formulae of ionic compounds. And they introduce valency as, look at this, it says the size of the charge of an ion is a measure of its valency. This is how it's written in your book. All right, so now that we have an idea of what valency is and how it links to the charge of the ions formed when these items combine in ionic compounds, we can start predicting the formulae of various combinations of atoms and in the compounds that they form. That's nothing special here. For example, let's see some examples here. Formulae of ionic, and of course, we're going to see that the same applies for covalent compounds. So the charge of an ion is a measure of its valency. This is the definition that, or the description they give in your book, so let's have it there. And we need to bear in mind that when atoms combine to form a compound, when atoms or ions combine to form a compound, the overall structure must be neutral. This is a very important aspect, a very important characteristic to remember. So let us look at these examples. We have here a compound which is made out of a magnesium and 2 chlorine atoms. Actually, this is an ionic compound, so when the two combine, actually they form ions. So we have a magnesium ion and 2 chloride ions. And let's see, why is it written as magnesium and these 2 here? Let us see why. Let's find the magnesium first. Where is the magnesium? Look at the magnesium here. It's in the second period, principal period, group, the second group, principal group of the periodic table, which means it's given the valency of +2, or the ions. When these atoms form ions, they have a charge of +2. So magnesium actually here in this compound would be in the form of an ion with a charge +2. And the chloride, here's chlorine. So when it combines through an ionic bond with a metal, this would be a chloride ion. And chloride ions have a charge of -1. So this is how we symbolize a chloride ion. But because now, remember that now the overall structure has to be neutral. So all this should be a neutral structure. But now if this has 2+ and this one has 1-, this is not neutral anymore. Overall, it has a positive charge, isn't it? So for us for this to become neutral, we need 2 of these chloride ions to combine with 1 magnesium to give us this neutral structure. And with formula that we write as magnesium chloride this way. And also, we could figure this out from what we met in the ionic bond. Why does the magnesium combine with magnesium atoms combine with chlorine atoms? Because the magnesium can give, it has two outer electrons. The magnesium has two outer electrons, and the chlorine, each chlorine atom has seven outer electrons. 1, 2, 3, 4, 5, 6, 7. So you see, if a chlorine atom picks up one of these electrons from the magnesium, if this goes there, and another chlorine atom that also has another 7 electrons in its outer energy level, so the other one goes there. So then the magnesium will get rid of these 2 electrons, will become an ion and smaller, of a smaller size, and we'll have 2 chlorines which will pick up those electrons from the magnesium, and this is how the magnesium chloride ionic compound forms. So you see, we do need, whether we see it, in other words, through this lens of how the electrons are rearranged there between the 2 species, or if we look at it through the valencies, we'll end up with the same kind of compound, isn't it? So this is how we justify how we write this compound in terms of valencies. By the way, let's stop sharing, because I'm afraid in case I confuse you. All right, guys. People, do you understand what we're saying here with the valencies and how we write the magnesium chloride compound? And what the valency represent? I mean, are there any questions up to now? I mean, are you following? Because I don't know when you came as well, if you missed the beginning. Okay, let's see. All right. So since, let's share again. So since now we're supposed to have the general idea, let us see some examples. Oh. We can do this example, or we can do, let's do this exercise, which is from this workbook that accompanies your book. It's on page 34. Now, in this exercise here, it says formulae of ionic compounds. Now, they give us, the table below shows the valencies and formulae of some common ions. They give us some positive ions and some negative ions. The positive ions, of course, are metals, and they also give us the formulae of some compound ions. You remember last week we spoke about compound ions, which are clusters of atoms, but they have gained 1 or more extra electrons, and they have become, some of them are negative ions, like this one, like the nitrate or the hydroxide. And there is also one very important positive compound ion, which is the ammonium. So we're going to use this, I hope you can see clearly the charges, because we're going to take the charges to represent their valencies. Okay, so we are given now this formulae with their charges, and we are asked to use the information in the table to work out the formulae of the following ionic compounds. First, copper oxide. Well, copper oxide, obviously it's a combination of copper and oxygen. Copper. So we write first the copper and then the oxygen. We start with cation first, the positive ion. Okay. So the cation is the copper here, and the oxide is the oxygen. Oxide. Now, we need to find their valencies or their charges. if they have the same charge, both of them, but opposite, of course, we don't have to write any other numbers here to indicate how many atoms. There will be one copper atom and one oxygen atom. And if we look at copper here, copper, they give it to us as having a charge 2+. I hope you can see those numbers. Let's make it a bit bigger. You see, they give us copper to have a charge of 2+, or valency 2. And oxygen, now from the negative ions, has also a valency 2, because you see this 2- there, it says 2-. So because they have the same valency, that if we write the compound in this form, copper oxide, it's correct, because it becomes a neutral compound. So this is the formula of the copper oxide. Now let us do something more complex, because it's already 11:52 here. Like, let's say silver nitrate. Let's do the silver nitrate. We first write the symbol for the silver, and then the symbol for the nitrate. If you it's also a compound ion. Here it is. And now let us look at the charges or the valencies. Silver, where is silver? Here it is. It has a charge of +1. So it has a valency of 1. And the nitrate has a valency of -1. So it's +1, -1, which means this, I wrote it too far away, but nevertheless, the formula for silver nitrate is this one. We don't need to write any other extra numbers here to identify, to indicate how many atoms of this or how many compound ions of that we need. It's 1:1. So the ratio is 1:1 because they have the same valence. The one has +1 and the other one is -1. So the ratios is in which they combine is 1:1. All right. Then let's see, magnesium bromide. Magnesium bromide. Let's write a magnesium. Where is the magnesium here? It's obviously, magnesium is a metal. Okay, so it's a cation. It has a charge of 2+. And what is the other one? Bromide. Bromide is one of the halides. And it has a charge of 1-. So, okay, so the magnesium, we said, has a charge of 2+. Here it is, 2+. Whereas the bromide ion has a charge of 1-. So we see here, they don't have the numerically the same charge. So we need to add, for every magnesium ion, we need to combine it with 2 bromide ions, so that its charge becomes altogether, if this is multiplied by 2, the total charge will become neutral there. So magnesium to bromide ions combine in a ratio of 1:2. Okay. Ammonium sulfate. Let's do the ammonium sulfate. Look at the ammonium. The ammonium now is a positive ion, so it has to be written first. Remember, positive ions are written first. So there is the ammonium ion, and it has a +1 charge. And the sulfate is a negative ion, so it will be written next. Here's the sulfate. Let's write its symbol first. But now the sulfate has a charge of 2-. So 2-, which means this lot, the way we have written, is not neutral. So how many, we have to have 2 nitrate, 2 ammonium ions. And because we need 2 of them, we put the whole thing in parentheses and we write a 2 there to say we need to have 2 ammonium ions combined with 1 sulfate ion to make a neutral structure. So this, I suppose, gives an idea of how these ions combine to give us the formulae of the compounds, and what we need to pay attention is that the compound that we are going to write down has to be neutral. So that is why we need to make sure that we to know about the charges, which are the valencies, and see where we must add 2 or 3 or more. Let's, what else? The magnesium nitride might be a good idea to write down. Magnesium nitride. Now, the magnesium, of course, is here it is, it's the cation. It's written first. Let's write magnesium. And now the magnesium has a charge of 2+. The nitride, be careful, it's not nitrate, it's nitride, which means it's just a nitrogen ion. Where do we have the nitrogen, the nitride? There it is, nitride. Look at this, it has a charge of 3-, yeah? But nevertheless, this is its symbol of the nitride, and it has a charge of 3-. Now, how do we make this structure here neutral? We have 2 of these and 3 of these. How can it give us a total charge of 0? We have to multiply here with some coefficients. So, but this is not really a problem there's no need to do calculations. We see this is the valency of the nitride, we write it here. And this is the valency of the magnesium, we write it there. And now you see if we have 3 magnesiums with this valency, and 2 nitrides with a valency of -3. So 2 times 3 plus this is 6 minus 2 times 3 is also 6, so that it gives us 0. So you see what we do here. Simply we write here the valency of the second one, and in the second one we write the valency of the first one, and we have our neutral compound. The correct formula of the neutral compound, the way we have to write it down. What else can we write? There's no, not the others are all more simple. The magnesium nitride, I think, was the hardest to write here. Potassium phosphate. Let's write the potassium sulfate. No, yeah, phosphate, not sulfate. Potassium phosphate. Where is the potassium? Here's the potassium. Potassium, and the phosphate is here. It's an ion with a charge -3. So potassium and the phosphate, symbol for the potassium phosphate. So you see the potassium, the phosphate has a charge -3. So we will simply write here 3 because the potassium has a charge only 1. So here we don't have to write the 1 there. So here is the correct formula for the potassium phosphate compound. So 3, this one has a charge of -1, this is -3, so just write the 3 there. So the moral of the story is when we write two ions rather, X and Y, the one has a valency of A, alpha, let's call it. The other has a valency of B. What we do when we write them next to one another, we write the valency of the second one as a number here next to the first one, and this is going there. So B goes there and A goes there, like an X.